Okay, so you have, you have looked at the transistors, right? You have seen how they use the transistors to make logic gates, like the NOT, the inverter, the NAND, and then the AND and stuff like that, right? Now we are going to see how to use those logic gates to construct complex digital systems like the decoders and then the encoders and then stuff like that. Right, so and then again, this is our goal is that we are going to design this at the end of the semester. Right? So this is the components within this is the components within the CPU, right? And then you know that all these components are made up of logic gates, but they use those logic gates to construct digital systems that are used within here, right? So first we are going to look at how to use these logic gates. You know what these are already. You know what the buffer is, the AND or XOR inverter now, no, right? Do you know what the buffer is? What is a buffer? Buffer. I mean, you can just look at the truth table and tell what it does. Huh? End gate. The first one. End gate. Or gate. Master, I said, what does the buffer do? The buffer. Yeah? So, so the buffer is a very important component in a digital system. Right. So when you look at the truth table, when A is 0, what happens to the output? When A is 1, what happens to the output? So it's just passing A to the output. And then what is the use of that? Hmm? Oh, massa. The switch is like the inverter. Hurry up. Just, what do you think it does? Not entirely. Anybody else? What does it do? Just look at the truth table and tell me what it does. The last person. Hmm? So you see that this is just the buffer, right? It's passing the signal just through it, right? So each gate is made up of transistors, right? And once you are sending a signal from one end of this transistor to the other end, there's a kind of delay, right? So this gate just delays a signal by some amount, right? So you give it an out an input, it delays the signal by probably 1 nanosecond, and then the output comes here. Very, very important circuit. If you want to delay a signal by some number, so if the delay within this gate is 1 nanosecond, and then I want to delay a signal by 3, I need to use 3 of this, and I've been able to delay that circuit by probably 3 nanoseconds. Understood? So essentially, what you're looking at is combinational logic. And then combinational logic just means that you are using the gates, the basic gates you have seen to construct digital systems like decoder, multiplexer. You know what a full adder is, and then you know what PLA is, stuff like that. That's what you use it for. So that's what combination logic is. So and then here you are hiding the unnecessary gate level details from the designer, right? So if you use a decoder, you must know that there are some gates inside the decoder, but you don't really care about them like that. You just care about the input and the output of the decoder, right? So we're going to see how to use these gates to design first the decoder. So in digital logic or system or whatever, what is a decoder? And don't say your DSTV is kind of. What is a decoder? I think you guys might have seen it before. So what? You have seen it before, right? And what does it do? Like, I mean, basically, what does a decoder do? Breaks down signal. Anybody else? A decoder. Yeah, that's what. So, I mean, here in digital system, all we are looking at is if I give it an input, what happens to the output? So, always think in terms like that. So, if I give an input, what happens to the output? So, what is a decoder in terms of that? I mean, close here, but not a single input. I mean, if it's a single input, how does it select the output? Yeah, of course. So. Anybody else? Uh-huh. Uh-huh. Mm. That is what every digital system does. It receives some form of input, conveys some form of output, but there are differences. So what does the decoder do? So it receives input, what type of input, and it does what? Yeah, a what? Analog to digital. But you are in another dimension, the most high dimension. Okay, so basically, right, this is how a decoder looks like. So you have your inputs here, then you have outputs. So input is here, output is here. Right? So now the decoder is an input pattern selector. So you put an input here and then you get an output. Right? Now uh, you can use your input to know how many outputs are there, or you can use your output to know how many inputs are there. What it does is that the input selects one line here to be active, right? So it's an input pattern. If you give it some input here, let's say 00 here, only one line can be on. The rest will be off. So it selects one line out of so many. Just like your DSTV, right? You have so many channels, but you can actually watch one at a time. That's just a decoder, right? So based on the input, only one line is selected, or is activated, or is on. The rest of the lines are off. Are you clear? No, 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 no. Only one can be on. So it means that you have selected one. So based on the input, you select only one of them. So it's an input pattern detector here. Are you clear? Have you seen how it works? Are you envisioning like as I said, like your DSTV, right? You have so many channels, probably hundreds of them, but you can only watch one. So based on the inputs you press, you have select. Yeah. Okay. Mm. Okay, but this one doesn't work. This one doesn't work there. Okay. All right. Do you guys understand? So essentially, right? If I have two inputs here, right? If I have two inputs, right? My number of outputs is based on these two inputs. So if this is n, so the number of outputs is equal to 2 to the power n. So if I had two inputs, the number of outputs is 2 to the power 2, which is what? 4. If I have three outputs, my number of outputs is what? Hey! If I have 4, don't say 8, 16, right? 2 to the power the number, right? Okay, so now let's study this truth table here. Now the inputs is A1 and what? A0. And then my output is what? Y3, Y2, Y1, 10. Now, if we study it carefully, right? If the input is 00, what happens to the outputs? Y0 is 1, the rest are 0. So it has been able to, like you detect only one. Based on the input, only one of the output is activated or is on. So if the input is 1, 1, you see that only Y3 is on. The rest are zeros. So this is how the decoder works. Yep.
In case I'm also trying to take and I start with Y3 as one and is it the same as
No, no, so that one, it depends on how you are designing it. Yeah.
okay?
It's your choice. But only one of the outputs can be on at the time. Are you clear?
Yes, sir.
So this is a symbol of the decoder, and this is so if you have something like this is a 2 by 4 decoder. It means that once it's something like this, it means that it has two inputs and what? Four outputs, 2 by 4 decoder. And then the inputs will be labeled like this. This is 00 is Y0. Have you seen it already? 01 is Y1, 10 is Y3, and 11 is what? Y3, right? So stuff like that. Do you understand?
Yes.
So now the important thing here is that how do I use logic gates to design what is inside the decoder? So if you're looking at the high level, right, this is what the decoder is. You know the inputs, you see the outputs. But what is inside there? What gates are used inside there? How do I use the logic gates we have learned to design the inner architecture of the decoder? I mean, you guys have done this already, then Boolean logics and stuff like that. So it shouldn't be a difficult thing at all. And so, based on the truth table, how do I design the decoder, the inner architecture of the decoder? How do I go about it? Anybody? What gate? What gate? So yes, yes. Uh-huh. Once you're giving something like this, right? So you now start thinking, look at the output and then look at the inputs, right? And then look at the gates that will best fit the input. So let's take 00. Right? 00 gives us an output of 1. So if let's say I'm supposed to guess and then I say an AND gate, right? I have A1, A0. A1 is 0, A2, A1 is 0, A0 is also 0, right? What will make this what will make the output of, so, and then we have to care about output. So here we are using y0. 0, 0, you see that it only turns on y0. So that's what we care about. So what will make this one 0, 1 here? What input will make this one 1? Eh? No, no, no. I'm using, this is an AND gate, right? I want here to be 1 based on A1, A0 being 0, 0. What must I do here to make the output 1? I invert that. So I take A1, I invert it. I take A0, I invert it. So if here is 0, the output of this inverter is what? If here is 0, the output of this inverter is 1. So the output is what? Simple as that, right? Do you understand? So a 0, 0 will be inverted and then the Y0 will be selected. So simply, once you have an inverter there, you can just simply make your circuit like this. Put a 0 here, 0 here. Understood? You understand? You see how easy that is? So the next one, let's look at y. We have done y0, right? Let's look at y1. The same AB. So for y1, A1 is what? 0. A1. A1 is 0 and A0 is what? Second. So if A1 is 0, this is A1, right? All I do is I invert this and then keep this one. And then this is my Y1. Then Y1, 2. The same AND gate. We have A1, A0. A1 is what? 1. So A1 is 1. There's no inverter. A0 is what? So you put. So you see how easy that is? Or it's difficult? So Y3, the same AND gate. But here, there is no inverter because 1 makes it on. So here, so A1, A0. So this is just a simple circuit for, yeah. No. So we care about where we have a 1. So for A1 is 0 and A0 is 1. Where Y is 1, where the Y's are 1 is Y0. So we take Y0 and then we draw the AND gate. And then we go to the next line. Is A1 is 0, A0 is 1. Where is 1? Y1. Look at the output. So you are relating the input to the output. Understood? So now it means that in effect, so you can combine this one because you have A1 here, A1 here, A1, A1. You just join the lines together. You have A0, A0, join the lines, and then you can now pass your signals through the circuits. You will always see that if I give it 0, 0, only Y1 will be on, all the rest will be 0. So here, if I give all the circuits 0, 0 here, right? You can see that only this one will be on, all the rest will be off. Stuff like that. Understood? So in effect, this is how it will look like. And then it's the same as this one, it's just that you have just separated it. So this is a typical, the inner architecture of a decoder. You have used logic gates, the AND gates, and then the inverter to design your decoder. Easy, right? Are you all there? You have seen how easy it is. So it's not any complicated. If you hear a decoder, it's not really that complicated. It's just this. Shall I continue? So now here, if I pass, let's say 1, 0 to it, you can see that only the third AND gate is on. The rest will be off. So what do you think we can use the distance for? We can use the decoder for in digital system. Pardon? Oh no, I mean in digital system, what do you use a decoder for? Yeah.
It
Mm,
has like a relay.
so. Oh, master.
Select.
A relay in digital system. You are taking yourself of analog systems and stuff like that. But let's see something like this. Let's see if you take memory, right? I drew memory like this, right? Right, and then I said there's only one line to here. I guess one line. It means that we have addresses, right? It means that when we take memory like this, you can only read from one location at a time. You can also write only one location at a time, right? Because of the addresses, and then because of there's just one line, right? So what you do here is that you can, if you have like just four locations, so from 0 to 3, right? All you can do is you have two inputs and then you have four outputs of a 2 by 4 decoder. Then you connect each line to this. You connect each line to each location. So now if you give it here 0, 0, only one line will be on. If you give it 0, 1, only one line will be on, and the rest are off. So it means that in effect, you can use your decoder to read or write memory, one location at a time. Understood? Now you can also use the decoder for your now if you know that your for machine code right there. Yeah. Mm. Yeah, so if you see a bus like this, right? Right? If you see a bus like this, right, uh, it doesn't mean it's 1 bit. So based on the architecture of the CPU, buses start from I think 8 bit to probably 32 bit, right? So it's not just some one wire to it, right? It starts from 8 bit to 2 bit, so you can take 8 bits or two to 32 bits. Understood?
Yes, sir.
Then the other use of the decoder is that you know that once you take your machine code, right, as probably you guys know that the machine code has sections, right? There is 0000, right? It has sections, right? With each section having a meaning, there's a section called the opcode. I think you guys must have seen it before. Opcode. And then the opcode determines the instruction you are doing, right? So now your CPU can do an AND operation. It can do probably AND or XOR, add, sometimes multiply, divide, it depends. And then a lot of operations. So these operations depends on the opcode. So how would you know that? So I can use a decoder, right? Then I connect the opcode to the input of the decoder, and based on the input, one of this one can be selected. You must know that your CPU, the operations of your CPU is that it can only execute one instruction at a time. You know that, right? You know that, like just one instruction. So that's why your CPUs are slower than probably your GPUs. You guys know the difference between a CPU and a GPU. All right. So the next thing is what? A multiplexer. So we have seen how to use the logic gates to design a simple decoder. Now, what is a multiplexer? You might have seen this one too against some digital system. Yeah. Okay, exactly right. So what's your decoder? What your multiplexer does is that let's say there is a single road and then there are multiple lanes like cars coming from these locations, right? But only one road, right? So only one car can move on this road at a time. So what happens is that you must have something here to select which one passes through. Or probably some police guy will be standing here, right? Right? And then that person will be selecting which car passes through. So that is an example of a multiplexer. But the most important thing here is that uh, how will he actually select which one to go through? Right? Now we have something in the multiplexer called the selector. Right? So it is the selector you use to select which one goes through. So now based on your number of inputs coming in, that will actually determine the number of selectors you have. Do you understand? Do you understand? So if you have something like this, so this is just the symbol of your multiplexer. So you have multiple inputs, and then you have one output. But as I said, the most important one is the selector. So it comes here. So you have inputs, four inputs, you have one output. So what do you think? So this is 4 bit input, right? One output. What do you? How many bits do you need to address the 4 bits? 2 bits. This simple exam question. So take note. Ah, you just guessed. Do you understand? So if you have 8, don't say 4. 3, right? If you have 16, so you guys see how it is done. 2 to the power, just the same 2 to the power n. So this selector is very important. It's what will determine or it's what will let route one of the signals through to the output. Right, so now this is the truth table of your typical 2 input multiplexer. So here, the 2 input multiplexer just means that you have 2 inputs, right? And then what is the select? How many bits? Just 1 bit, right? So you have input D1 and then you have input D0. And then you have output, probably Y. And then the select line is the S there. Right? So what do you notice in the truth table? When S is 0, what is the output? Look at the output. There are several zeros of S. So when S is 0, what happens? What happens to the output? No. Look at S. If when S is 0, what happens to Y? Master, don't look at me. Look here. Eh? Alternates what? Pay attention. When S is 0, what is Y? Just observe. So let's start. When S is 0, the first line, Y is what? 0. The second line, Y is what? 1. The third line, Y is what? 0. The next one, Y is what? 1. Now observe the inputs. When Y is 0, 1, 0, 1, what is the input?
The value of D0 is kept when
Yeah, so when S is 0, you route the input D0 to the output. You see that it's the same. You see that this is the same as D0. Have you seen it? Have we seen it? Yeah, I think I have some pointer so that you guys see it well. So here, you see when S is 0, right? D0 and Y are the same. Have you seen it? When S is what? 1, D1 and Y are the same. You see how simple that is? You just have to look at the truth table and then you can use that to. Okay, so this is the symbol, as I said, of a 2 by 4 multiplexer. And can you use any logic gates to design the inner architecture of this? How will you do that? By looking at the truth table. How will you even start to conceive of that? Okay, you can draw it and let me see something. Just look at the truth table, observe the truth table carefully, and look at how you can use any logic gate at all. Are you done? Master. Okay, that's right. So now let's see. Okay, I have my what? Y, right? Right. So, and I have S. And then I start with D0, right? So, connect this to an inverter here. So, if it's 0, this one is rotated through. Is that clear? So I have my S here, right? So if this S is 0, right, here becomes what 1. For an AND gate, when one of the inputs is 1, the output directly depends on the other input. So because here is 1, the output is whatever value this is. So D0 has been rotated through. If D0 is 1, here will be 1. If D0 is 0, here will be 0. Based just because here is a 1. Understood? Do you understand? So in the same way, another one, I have S, the same S, right? But here there's no NOT gate because I want it to be 1, right? And then D what? D1. So it means that when S here is 1, the D0 here, D1 here will be routed to Y, right? But here there's only one Y. This Y and this Y are the same. How do I connect this together? Now don't say this. I mean, you have created some kind of a short circuit, right? So this Y here, and then this Y are the same. So how do I connect them together? Which gates can I use to connect them together? Huh? the OR gate, right? So they will be Y. Do you understand? So I can now connect this S and this S are what? The same. So I can connect this S together. S. Right? So what that means is that essentially if S here is 0, if the input S here is 0, right, it means that this place is what? 0. Automatically, once for an AND gate, once one of the inputs is 0, the output of the AND gate is 0. Understood? So now if here is 0, this place become 1, D0 is routed through. Right? Now for an OR gate, if one of the inputs is 0, the output depends on the other input. So this 0 will be routed here. If S is 0. Have you seen how it has worked? Now if here is 1, right? This inverter will invert the 1 and make here what? 0. Now for an AND gate, once one of the inputs is 0, the output is automatically 0. Right? Why are you laughing? So now this one comes here. This here is 1. D1 will be routed to here. And because here is 0, D1 will come to the output. So essentially you have been able to use AND gate, OR gate, and an inverter to design your multiplexer. That's how simple it is. I think you guys might have done these things already, so this is how it looks like. I mean, this is not important. This is not important. This is not important. So I'm skipping all of this because we don't have enough time like that. Okay, so now with what we have done so far, right? Okay. Now let's look at this one is also important. The comparator. You guys know what a comparator is? A comparator. I mean, this is the name. So if you have two inputs A, B, so what your comparator does is that it compares A and B, and if they are the same, it gives an output of 1. If they are different, it gives an output of 0. Right? Simple as that. So here is what? Here's what? Here's what? Here's what? What gate is this? Hmm? So, probably. So this is just a symbol of a comparator. Then this is like a 4-bit comparator. So I can use the I can use this game. Why are you laughing? So this is the architecture of the inner construction of a 4-bit comparator. You don't have to go through that. So this is the example, the question I give, and then this one will come in your exam. So it's just something like this. So, right. So now I gave you what what did I give you guys?
One was and one was one was NAND.
It was something like this, right? So you have your ALU. The ALU has two inputs, A and B, and then it has one output Y, and then you have the function of the ALU, F, right? So now, based on the function, one of the operations will be done. So based on if the function is 0, 0, the function, obviously over there, the function is 0, 0, the the function will be a and b. So that's what you must do. If f is 0, 1, you must do a or b. If it is 1, 0, you must do a x or b. If it is 1, 1, you must do not of. You know that symbol is not of b. Right? So if I give something like that and then I tell you to use basic logic gates like encoders, decoders, or anything to design the inner architecture of this, it can be done, right? Based on, I mean, why you laugh? Based on what you have done so far, you have covered everything. You've done. Eh? Now, after that, you must pass those variable the 0 and 1 through the circuit and see how it works.
And we have output.
Eh? The output is y. Have you seen it there?
Maybe a value for y so that we can use two digits.
You want to have a value with the use trace, and it doesn't work that way.
That will make the person know that what you have done is correct.
No, no, you have an input. You have input AB.
Okay.
So what's the one column 0 beside it?
You have never seen that before. It means 2 bits. 0, 1, 0, 1, 2 bits. So if I have 3 column 0, how many bits is that? Don't say 3. How many bits is it? Huh? Hey. So if 0, 1, 0, 1 just means that I can have something like 0, 0. So just 2 bits, 1 bit, another bit, 0, 0, right? Hmm? Hmm? I say if you write something like this, right? It's like a bus, right? So it means that this bus is only 2 bits. One is to 1. 1 is to 0. 2 bits. If I have 3 is to 0, it means that this bus is a 4-bit bus. And I thought you guys understood this already. I didn't know that. So if you have in digital, and then this is mostly used in coding, like in Verilog or VHDL, right? If you code and then you are normally looking at registers or buses or variables. So if you say y, and then you say 1 is to 0, right? This just means 2 bits. And if I say 2 bits, I mean that I can address 0, 0, 0, 1, 1, 0, and 1, 1. Right? So I can have 4 locations within that 2 bits. Right? So that's 2 bits. So now if I have something like 3 is to 0, this is like a 4-bit bus or a 4-bit variable. So it means that I can address from 0, 0, 0, 0, that is 4 bits, right? Up to 1. The highest will be 1, 1, 1, 1. Right? So I can address numbers from 0 to what is 1, 1, 1, 1? Convert from binary to decimal. What is 1, 1, 1, 1? Ha! 0 to 15. Oh. Okay, so here, what I can do here is that so if I'm giving something like this, right? If I'm giving something like this, right? And then I say, oh, use logic gates or whatever to design. My first thing is the first thing I have to think about is a multiplexer. That's the first thing that comes to mind. The multiplexer. And then this multiplexer, I said, selects between different options, right? So if you have different options to do from. So here I can do what? And I can do or, I can do X or, I can do not or whatever. Right? So I can now connect my gates here. So this is, my first one is AND. So I can connect an AND gate here. Then this is A, B. I can connect an OR gate Actually, there's all gates here. I can connect an XOR gate here, and I can connect an inverter here. This is P. And then this is my F or whatever. And this is the output bar, right? And then I just come and say, okay, here is 0, 0, 0, 1, 1, 0, 1, 1. So if F is 0, 0, so it means that I'm doing A and B will be right to the output. It's simple. This is just like some 10 marks, and then you are done. Eh? Oh, it will come. Don't worry. Are we done? Okay, so this is the ALU, right? And then the ALU can do different functions. Now another important gate is have you guys heard of a tri-state buffer before? Tri-state buffer? No, nowhere. You have never heard anywhere. You guys, your computer engineering is some way. Your computer engineering will So, okay, the most important thing is that you see that for all the gates, if I take an AND gate, as long as I give it an input, I get an output. As long as it's an input, right? So if I give it 0, 0 here, automatically the output is 0, right? So the output of all the gates we have looked at is either 0 or what? 1 based on the input, right? And then sometimes the output is unknown. And if I say unknown, what does that mean? So there's a symbol called is X. So if you see in any digital logic book, the symbol X, it means that the output is unknown. And if you say unknown, it means that the output can be either 0 or a 1. What? I mean, there are several cases. For instance, if you have an OR gate, right, and then you give one of the inputs 0, and then you leave this output out, you know that the output of the OR gate will not depend on this value. So this value is either a 0 or a 1, but you don't know what it is, right? So that's one. That's one. So anytime you connect an input, it's either 0, 1, or unknown. Unknown just means 0 or 1, but you don't know what the value is, right? But sometimes you want the output to actually float, right? So you have a gate called the tri-state buffer. So there is an enable here, then you have A, and then you have your output. So if the enable is 0, right, it means that no matter the value here, right, the output is known as high impedance, Z, high impedance or floating. The value is not 0, it's not 1, it's high impedance. It's floating. It means that you have actually disconnected the wire, something like that. Understood? If the output is, if the enable is 1, right, it means that any value here will now be routed to the output. Simple as that. So this is like some enable, and you know and what an enable is? An enabler. So if it's 0, it's kind of deconnects the output from the input, and then the output is left floating or at high impedance, but not 0 or 1. But where will you use something like this? Yeah? So the place where you use something like this is just within your system, right? So you know that within your system, your laptop, whatever pieces, there's just one bus. This bus connects your CPU, memory, input, output, right? Just one bus. Now the rule is that only one device or only one, either the CPU or the memory, can use the bus at a time. So if one is using, the other must lay idle before the other one finishes, and you can use it. So you can use the tri-state buffer here. So if CPU wants to use the bus, all CPU has to be that. You see the gate CPU on top there, the enable there. The gate CPU. So this uh, this is your tri-state buffer. Hey, I'm tired of it. This 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 is your tri-state buffer, right? You see that this is the enable here. So if CPU wants to use the gate, all it does is that it makes here one, and then whatever whatever data the CPU has, it can be kept on the bus. And if CPU is not using the bus, all it does is it has to make here 0, so that here is left at floating or high impedance, and then any other then here too, if this one wants to also use the bus, it also enables here, and then it can use the bus. So that's the one use of the tri-state buffer. Right, so you can use logic gates to design your tri-state buffer. I don't care about it. So now so the last thing is this. Right, you have what is known as the priority circuit. You guys know what a priority circuit is? Digital system again. What did you guys learn in digital system? What did you guys learn there? So essentially, right, priority circuit. How do I even explain it? Now, if you take again the bus. So this a real example, right? So if you take your bus within your CPU again. So you have CPU, you have, let's say, memory, you have input output, and then you have some other hardware accelerators, right? Probably GPUs, everything connected to the same bus, right? And as I said, only one component can use the bus at a time. So in the real world, right, what happens is that the CPU has a connection. The CPU has a connection to the bus called the request line. So it has a line to the bus called the request line. So if the CPU wants to use the bus, right, it activates this request line, and then there is kind of circuit here that will actually give the CPU chance to use the bus. So what the bus does is that there's a connection from the bus to the CPU, which is known as the grant line. So you have request and grant. So if the CPU wants to use the bus, it will request, and then it will request. If I say it will request, that means that it will make this line 1, activate this line. And if the bus is free, this line will be 1. The grant line will be 1, and then the CPU can use the bus. Now, all other components have the same connection. So we have the request. We have the request from the memory also. Request, then grant. Right? So now if the memory also wants to use the bus, it has to request. And then if the bus is free, it will be granted, right? The same with I/O, the same with the accelerators or whatever connected to it. So now the most important question is if the memory and then the accelerator request grant. So if the memory requests the bus and then the accelerator also requests the bus at the same time, here's one, which grant line will be activated? So am I the one answering in my head or not? Or I was just trying to think out loud, and I just memory, because I know that if I say if CPU requests and then memory requests, everybody will say the CPU. So if I say memory and accelerator, here's one. They request to use the bus at the exact same time. What happens? The memory will do what? Why? Hmm? It does what? How does it come before the accelerator? Okay, so now I'm just changing the. So it means that the accelerator will be because the one comes in first. Nah,
Has higher priority.
they have not assigned any priorities here. So I mean, but yes.
Of what I think, the CPU is actually requesting information, let's say information from the memory.
No. Here the CPU is not involved anymore. The CPU request line is zero. So it's memory. That is the memory and accelerator.
So the accelerator will definitely work on what the memory has given out.
Yeah. So basically, what happens is that before, even within your CPU, right, your bus has, before the chip is actually even made, each component there is given a priority. So CPU, of course, always has the highest priority. So let's say three, right? But then any other components will, so it will assign priorities to, let's say it gives two to memory, one to accelerator, and then zero to IO, right? So anytime, if all the components request the bus to use at the same time, the CPU will be given the bus. Then the CPU must finish operation before any other component can use it. But you see that if if it is the CPU, fine, because I mean probably it is using the bus for something. But some IO can actually hijack the bus. And then just once it is given the bus, once it has the high priority, once it is given the bus, it will use the bus for probably for 100 years, and then so it means that you can have some errors within your PC. It means that some kind of company has hijacked the bus. So now they have different methods to actually prevent this, right? And then, but that is beyond the scope of this. So probably if you're going to study for your masters or something like that, you can go into that, right? Okay, but now essentially, so what happens is that within the CPU uses what is known as the priority encoder to do all of this. So it assigns some kind of importance to each of the components. So now let's look at the truth table here. A3, A2, A1, A0 are the inputs. So let's say that A1, A3, A2, A1, A0 are the request lines from CPU, accelerator, IO, or memory are the request line. And then Y3, Y2, Y1, Y0 are the grant lines. Right? So I give it an input. So one input is activated, the request is activated, and then it can only activate one of the lines of the outputs, right? So when you look at this table, right, which one has the highest priority? A3, A2, A1, or A0? Why?
Because A3 is 1, Y3 is 1.
Then which one has the next highest priority? A2. Which one next? So you see that when A3 is 1, the grant for Y3 is just 1, always. Unless it becomes 0. And then the next one is what? A2, right? The next is what? The next is. So A0 has the lowest priority. So can you draw the circuit for this? So based on this truth table, right? If anybody can draw the circuit, I will give you 20 marks. Yeah, you just draw it. Then we are done. 20 marks free. Just draw the circuit for this. Use logic gates. Just AND gates. Just. So just think about it. Just start with the output. So let's start with A3 and Y3. So put your output out. Y3, right, comes in. And then we have what? A3. Right? So this is just the connection from Y3 to A3. Just a line, because when Y is 1, directly Y3 is Y3 is 1, right? Is that right? Now, so go to the next. Y2, right? What happens? So Y2, we are looking at A2, but A2 depends on A3, right? So we have A3 here, this A3. So if I use an AND gate here, then I connect an inverter here. So what have I done here? So what have I done essentially? So now, if A is 1, what do you think happens? So 1 has come here, right? And then here is 0. This one is deactivated. So here becomes 0. If here is 1, here becomes what? 1. Now let's go over again. So if here is 0, what happens? So here is no longer 0. This 0 comes here and becomes a what? A 1. And then A2 will be understood. So if here is 1, here becomes 1. So it means that A2 depends on A3. As long as A3 is 1, A2 can never be activated. Have you seen it? As long as A3 is 1. So I've done the first one for you. So what is next? Y, Y1. The same exact way, right? You have an AND gate. You have your A1, right? But you must know that A1 depends on, it depends on both A1 and A2, A3 and A2, right? So as long as A3 or A2 is a 1, this one can never be activated. So A3 must be 0, A2 must be 0 before A1. Simple, then you can do that for
That means that A1 takes 3 inputs, or we have to
yeah,
avoid
3 inputs. And then the next one will be 4 inputs, and then A3, A2, A1 will pass through a not an inverter, and then A0. So you see how simple is this? So we are done for the day. Pardon? Right. Any question?